Welcome back to Honors Topics in Physics and starting our next unit. So here we've got a truck which is stationary, and this guy is trying to get it moving, and in order to get it to move, he needs to do what? He needs to exert a force. And that's what this unit is about, forces. So if it's something is stationary, in order to get it to moving, you need to apply a force. But what is a force? A force is simply a push or pull on something by something. And does a push or pull, does it have a direction? If you exert a force, does it have a direction that you exert it? Yes, it does, which means forces are vectors, and because they have both a magnitude and direction. So since this guy got it moving and it wasn't moving, we say that the truck has done what? Since its velocity changed. We say that it has accelerated, and that's what forces do. That's what net forces do, is they cause an object to accelerate. Forces cause an object to accelerate in the direction that the force is applied. So since he is pushing to the left, this is going to accelerate to the left, and it would have a negative acceleration, because we typically think of left as negative and right as positive and up as positive and down as negative. So remember the three ways an object can accelerate. An object can speed up, slow down, okay, or change direction. So those are the three ways an object can accelerate: speed up, slow down, and change direction. And depending on the direction of the force, that's what the force causes the object to do. So if we push an object, if this guy pushes the truck to the right, the car is going to accelerate to the right. It will have positive acceleration. Okay, so it was moving to the right and it accelerated to the right. So if you push something the way it's moving, if it's moving to the right and it accelerates to the right, it speeds up. Remember what happens if something is moving to the right and it accelerates to the left. So we're going to push it to the left. What's going to happen if the acceleration and velocity are in opposite directions? Well, an object slows down. Remember that displacement versus time graph gets flatter. So we'll exert a force and we'll cause it to slow down. And the other way we can cause an object to accelerate is to change direction. So this is supposed to be an overhead view of a tractor trailer, and he's on the interstate and he's about to get off on this exit ramp here. So if we were to push the truck in the way it was moving, it would speed up. If we were to push the truck the opposite way it was moving, it would slow down. What's the other way we can push it? We can push it from the side, and that'll cause it to change direction. So here's my truck changing direction. So look at him catch that drift. So if an object is pushed from the side, it'll cause it to turn. Okay. What if we had two people pushing on each side of the truck equally as hard? Which way is it going to go? Left, right, up, down, in, or out? Well, if people are pushing on it as equally as hard, then those forces are going to cancel out. Okay, remember what would happen if we were to add these two vector forces? Let's say we had 5 newtons to the right and 5 newtons to the left. Okay, or 5 meters to the right and 5 meters to the left. That would add up to 0. So forces can cancel out if they are equal and opposite. And if the forces are equal and opposite, we say that they are balanced. Okay, if all the forces cancel out, we say that forces are balanced. Okay, if they are equal in magnitude and opposite in direction. Okay, so we already covered that. So here we've got two forces that are balanced. Okay, they are equal in magnitude and opposite in direction. Okay, what about these two forces? Would these two forces be balanced? Okay, they are equal in magnitude and opposite in direction, so they are balanced. What about these two forces? They are opposite in direction, but they are not equal in magnitude. They are not balanced. What about these two forces? They do look like they are balanced. Here we have two forces that are equal in magnitude. Do they cancel out? Are they balanced? No. They are equal in magnitude but not opposite in direction. These would not cancel out. If we were to add these two forces together, we would get a diagonal resultant force, just like before. We can add force vectors, and those are not balanced. Okay, so let's say we push a book and we shove it, and what's going to happen after I let go? What's going to happen to that book's speed? Okay, it's going to slow down. Okay, why does it slow down? Because there is friction. Okay. Friction tends to cause an object to slow down. Friction is an unbalanced force very frequently. So Galileo experimented with balls, spheres, and he rolled them, and he found that they slowed down very, very little over the course of a distance because there was very little friction involved. And he came to the idea that if there was no friction, that the balls would just keep rolling on forever and never stop or even slow down. So he came up with one of basically Newton's first law, which was that an object in motion tends to keep in motion and not slow down or stop unless something causes it to do that. This is directly opposite what people thought at the time. People thought that an object's natural state was at rest. So if you got an object moving, it would just naturally it wants to be at rest. So that's what happens. And it made sense, except for the planets. The planets keep moving, and they believed that the objects in the heaven had different laws of physics than the objects on Earth. So there was a different set of physics laws in space and in the heavens than there was on Earth. So along comes Newton to kind of formalize some of these ideas, and he's in his 20s. And he puts together basically what physics was before Einstein in his book Principia when he was 24. What we're learning now is Newtonian physics. Einstein came along and modified things with relativistic physics and things like that. But unless you're moving close to the speed of light, or near a black hole or something like that, Newtonian physics does a pretty good job of explaining how the world works. So Newton looks at what I guess he looked at what Galileo did, but if not, he did his own experiments, and he basically came to the conclusion that an object will move at a constant velocity unless there's an unbalanced force acting upon it. So an object's going to keep doing whatever it was doing, okay, until something makes it do something differently. It's not an object's natural tendency to go to rest. Okay? An object's natural tendency is to keep doing whatever it was doing. If it was at rest, it's going to tend to stay at rest. And if it was in motion, it's going to tend to stay in motion until an unbalanced force, a force that isn't canceled out by another one, acts upon that object. So which of these objects has a constant velocity? Does the red ball have a constant velocity? Is its velocity changing? No, its velocity is 0, and it's staying 0, so we'd say it has a constant velocity. So there are balanced forces only acting on this object, or no forces. Okay, what about the blue ball? Does it have a constant velocity? Okay. Does it have a velocity? Yeah, it does. Is its velocity changing? Does it seem to be speeding up or slowing down or turning? No. Then it's got a constant velocity as well. So that means that there's balanced forces or no forces acting on the blue object as well. Okay? There's no unbalanced force acting on either of these two objects. So if an object is stationary or moving in a straight line at a constant speed, then its velocity is constant, and you know that the forces on that object are balanced. So let's say I launch two very, very light ping pong balls into space where there's no wind resistance or anything. I launch one at 25 meters per second, and the other one I launch at a slower speed of only 3 meters per second. Which one of those ping pong balls is going to come to a stop first? The answer is neither. They're both going to keep moving on at whatever speed that they were moving at for infinity, or until they hit a planet, and that planet exerts an unbalanced force, or a star, or something along those lines. Okay, but once you get an object moving, it takes a force to stop it, not to keep it moving at a constant speed. So normally, this is when I would use my little kind of air-powered soccer ball kind of thing. It looks like a frisbee, and it's got fans underneath it, and the fans blow air underneath it so that when you give it a push, it rides on a cushion of air, and there's no friction between it and the ground. So once I get it moving, it keeps moving in a straight line at a constant speed because the forces on it are balanced. Okay? And so it behaves exactly like Newton's first law. When it's stationary, it tends to stay stationary. When it's moving, it keeps moving at a constant speed until an unbalanced force, like hitting a wall or something along those lines, causes it to change. Okay? We say this property of matter that resists changing velocity, or the tendency to keep doing whatever it was doing, we call this inertia, which is a property of matter. Okay? Bill. You can think of it as a laziness of matter to do anything other than what it is doing. It's on the couch, it wants to stay on the couch. Okay? Once it's moving, it wants to keep moving. It does not it doesn't want to change whatever it's doing. It requires a force to do that. So this is when I would typically set some plastic, not glassware, on one of the desks and put a tablecloth underneath it. And I would yank the tablecloth very, very quickly. And in a perfect world, all of my table settings and all that would stay on the desk, while the tablecloth is removed very quickly from it. And this is supposed to be a demonstration of inertia. The candlestick and the cup and the plate, they're stationary, and their tendency is to stay stationary. So when you give the paper cloth or the tablecloth a quick yank, there's not enough force between the tablecloth and the table settings to really cause it to cause its inertia to change what it's doing. Now, if you do it very slowly, you'll drag everything off with it. But if you do it very quickly, there's very little force between the objects. You can do this at home with your own table settings and tablecloth. Get parent permission before you do this. You can do it in a little more of a safe version of this if you take a playing card and you put it over a cup and you put a coin on top of it, and you give the playing card a quick flick with your finger. If you flick that playing card very quickly, the coin will fall right into the cup, because again, the similar to the tablecloth, the coin's inertia tends to stay where it's at, doing what it was doing, which was just sitting there. Now, after that, gravity takes over and exerts an unbalanced force and causes it to accelerate down. But so here's a couple ways that you can tighten if the hammerhead tends to keep falling off your hammer and you want to tighten it. There's a couple different ways you can do this. You can strike the hammer head down, okay, and what you'll do is you'll slam the hammer. You'll jam the hammer handle into the hammer head, okay, and then this should make enough sense if you just slam this down. But you can also tighten the hammer head on it by jamming it handle side down. And when you do this, what's going on is you get the hammer head and the handle are moving down. Now the block of wood stops the handle, but the head's going to continue to travel until the friction between the handle and the hammerhead causes it to slow down. But in the process, it will tighten on the handle. This is just a picture I thought was cool of a bullet slicing through a playing card. You can see that it's sliced through, and the top of the card isn't traveling along with the bullet yet, because even though this is very light, it still has inertia. This is normally where I do my tennis ball hat demo. You really have to see this one to explain it. So remind me to do the tennis ball hat demo when you guys see me, and I'll do it for you. Okay. Next, driving with and without your seatbelt. Let's see. So What I want you to notice is that the wall stops the car, okay, but the person keeps going as if there was nothing to stop them, which initially there isn't. Okay, the inertia of the person causes them to keep going. So if this car hits the wall at 60 miles per hour, as soon as the car is stopped by the wall, okay, you continue to travel at 60 miles per hour. Until an unbalanced force causes you to change your motion, which is your face in the steering wheel. It could be an airbag, could be a seatbelt, but this is what happens if you do not wear your seatbelt. Look at you just keep moving. Okay? Look at that impact. Ow. You do not want your face to hit the windshield like that. Now you can stop a different way. And you can have a seatbelt, and the seatbelt exerts an unbalanced force, causing you to slow down with the car, which is a much safer way to do this. See, they paint the dummy's face so they can see the imprint on the bag. So which way would you rather stop? Wear your seatbelt. Where's my, there we go. So here's another little lesson in Newton's first law. So apparently this truck, I don't know if this is faked or not, but I like the video regardless, or the picture regardless. So what you can see is this 18-wheeler was carrying a big block of stone, and the stone wasn't secured, and the truck came to a stop. And when the truck came to a stop, the block of stone kept moving, just like you in the car. When the car stops and you don't have your seatbelt on, you keep moving forward. So this is not a good example of how to secure your cargo. Whiplash is another example of Newton's first law. If you do not have a headrest behind your car, which all cars now are required to have headrests, but they didn't used to, then what could happen is if you were standing or if you were stationary at a stoplight, okay, and a car were to hit you from behind, okay, your whole body except for your head, okay, your back and your butt and your legs and your feet and all that are going to get accelerated by the car. Now your head is stationary, okay, minding its own business, and when the rest of your car of your body gets pushed forward, your head is stationary, just like the plates on the tablecloth, and its natural tendency is to stay put. So it looks like your head gets whipped back, okay, and that's what causes whiplash. But it's not that your head gets whipped back; it's that your body gets whipped forward, and your head is trying to just stay put, okay, and so this flexes out your neck and does bad things to your neck. Okay, another example. Let's say you're driving along at 60 miles per hour. You should not be doing what she's doing. That's texting or whatever she's doing on her phone, getting a phone call. So you're driving 60 miles per hour, and you drop your cell phone, and you want to drop it into the seat. What happens to that cell phone? Does it fall straight down into the seat, or does it hit the back of the seat? Okay. Well, try this sometime when you're on the interstate. Drop an object. It doesn't have to be your phone. You'll see that it drops straight down. That's because the phone is traveling at 60 miles per hour with the car. So the phone is going to naturally keep going with the car. It's not going to get shot back. Okay? So, and that is it for the day.